In this chapter, we're going to look at exponential functions and logarithmic functions. Logarithmic functions would be totally new. You may have seen exponential functions prior to this. But basically with an exponential function, whenever your variable of x is up in the exponent, it's considered an exponential function. The a here and your b end up just being different numbers that would be occurring in your particular problem. So for the one that's down below here, it's really a y is equal to a 1 times a 2 to the x, where your a would correspond to the 1, your b would correspond to the 2. Now, for an exponential function, your b here, whatever your exponent's on, always has to be positive and not equal to 1. So let's go ahead and graph a couple exponential functions. So let's make a t-chart for a y equals 2 to the x. Plugging in 0, you know anything to the 0 is 1. Plug in 1, 2 to the first. Plug in 2, 2 squared. Plug in your 3, 2 cubed. A negative exponent means remember you got to take the reciprocal, so it's a 1 over a 2 to the first. Here it would be 1 over a 2 squared. Here it would be a 1 over a 3 or 2 cubed. Then we want to go ahead and plot those points. Left 3, up an eighth. Left 2, up a fourth. Left 3 or 1, up a half. Then you're right here, and then over 1, up 2, over to x being 2, all the way up to 4, and then over to 3, all the way up to 8. And then you want to draw a smooth curve in, connecting all these. And then you end up getting this curved shape right here. This is the general shape of any exponential function. It continues to go up and to the right forever, and it levels out and goes out to the left forever. It has this basic shape, however it may be reflected, but it's still going to have the same basic shape. Well, we want to next take a look at the exponential function for this one right here in the graph of that one. So you plug in 0, half to the 0, half to the first, half to the second, which would be a half times a half cubed, and then you'd have a negative exponent, which means you got to flip this, so it really ends up being 2 to the first. Negative exponent, so you got to flip it and then square it, flip it and then cube it. So then you want to go ahead and plot these points if you've not done so, and then draw a smooth curve going between or over them. So then you end up with just this graph here. You'll realize that it's really the same shape as what we had over here on the left, but it's just reflected over the y-axis. So it goes up this way forever and goes down this way here forever. All exponential functions will have this basic shape. This first one here is referred to as a growth function because your b value, which was your 2, what your exponent was on, was greater than 1. It has a y-intercept of 1 because that's what our a was. Your a value here, when it's in this form, always tells you what your y-intercept is. This one here is a decay function because it goes down as it goes to the right. And that happens when your b is between 0 and 1. We want to look at these to decide if they are growth or decay. The first one here, remember we need to look at y is equal to a times b to the x. Now, if your b value is greater than 1, it's referred to as a growth. So here, what's your exponent's on is greater than 1, so we're going to say it's growth. So we also want to do that for the next one. We look at what your exponent is on and decide, is it greater than 1? If it is, it's growth. And then we'll do that over here. Is this greater than 1? The answer is no, so therefore it's not growth, it is decay because that value is between 1 and 0. Down below here we have an exponent raised to an exponent. You should remember when you have an exponent raised to an exponent, you need to multiply your two exponents together. In multiplying exponents, you need to multiply what's inside your roots together. So 3 times 5 is 15, so you get root 15. Over here, we are dividing. We could write this as a y to the 3 cube root of 3 over a y to the square root of 3. So 3 square root of 3 is an exponent, and square root of 3 down here. Remember, when you are dividing, you need to end up subtracting your exponents, whether it's written this way or this way. So we subtract our exponents. A 1 root 3 minus a 3 root 3 minus a 1 root 3 gives you a total of 2 root 3 as your exponent. So we need to go ahead and solve exponential equations. Exponential equations are equations where your variable is in the exponent. Here are two examples of exponential equations, and you notice in both of them your exponent or variable is in the exponent. What you want to try to do is to try to get the same base on each side. Here we have 4 to the power. Can we somehow rewrite this side here as 4 to the power? Well, if you just try 4 different powers on your calculator, you'll realize that on the right side, this is 4 raised to the 4th power. When you end up having both sides with the same base, the only way these can be equal is if the exponents are equal. So basically, you're kind of dropping the bases since you've converted them both to be the same. So you're going to set the two blue exponents equal to each other. Now you're going to solve this just by adding 2 and then going ahead and dividing by 9. And we end up getting 6/9, which reduces down to 2/3. We're going to use that same approach over here. We're going to try to get the same base on each side. We got a 2 to the power on the left, so that's not going to do anything. Can we somehow rewrite 32 as 2 to the power? And well, yes, we can. 32, if you know that in your head or play around with it on your calculator, you'll find is 2 to the 5th power. Since you have it as 2 to the power on the left, 2 to the power on the right, you can set the exponents equal. So you set the exponent on the left equal. And then over here on the right, remember it's an exponent raised to an exponent, so you need to multiply. So it's going to be your 5 times your other one. Distribute through. Combine or take your x's to one side, take your non-x's to the other side, divide by 2, and you get x to be 18. This would be an exponential inequality. We're going to still approach this the same way. We're going to try to get the same base on each side. On the left side, we have 5 to the power. On the right side, can we somehow rewrite 625 as 5 to the power? If you don't know that off the top of your head, you try a couple of things in your calculator and you'll realize it's really 5 to the 4th. However, it's 1 over our 5 to the 4th power. And we don't want it as 1 over, we just want it as 5 to the power. Remember, when you take your whole exponent up here, it becomes a negative exponent. So now that we have 5 to the power on the left, 5 to the power on the right, we can basically drop the bases and just deal with the exponent. So you're going to have this first exponent, followed by your inequality sign, followed by this exponent. Now we want to go ahead and add 4 to both sides. And you could also then subtract your 2k, or you could just go ahead and subtract your 3 and get down to this. Either way, you're going to end up getting this answer here. Just remember, when you multiply or divide both sides by negative, just switch your inequality sign. Looking over here, we're going to try to accomplish the same thing, try to get the same base. 3 to the power on the left. And then over here, we're going to try to write it as 3 to the power. You should remember that 27 is a 3 cubed. But since it's in the denominator, you got to bring it up, and then that exponent becomes negative. When you have 3 to the power on the left, 3 to the power on the right, you can just drop the 3's and work with the exponents. The blue exponent on the left greater than the blue exponent on the right. Now we can go ahead and solve this by subtracting a 3 from each side, dividing both sides by a negative 2, which switches your inequality sign. Now, here we're going to start out with a couple of points, and we need to basically work backwards and find the equation that goes through those points. So here's your general exponential equation. We need to make sure it goes through both of these points. Now, you were told before that this a here is the y-intercept. Well, if you go over 0 and up 5, that's really your y-intercept on your graph. So therefore, a has to be 5. So if we plug 5 in here, we'll go y is equal to a 5 times your b to the x. So now we're going to take a look at this other point. This other point is really just an x followed by a y. So I'm going to replace my x with 3, my y with 125 by plugging that point in. So the y goes with the 125, b, or 5 times b raised to the, not x, but 3. Now we need to go ahead and solve this. So I need to get my b cubed by itself, so I'm going to get rid of the 5 by dividing both sides by 5. Now I need to go ahead and take the cube root of 25. Or you could write it as 5 to the 2/3. You know that your 25 to the 1/3 is really a 5 squared all to the 1/3. And then it's an exponent raised to an exponent, so you'd multiply those exponents. So that's why you could write it as 5 to the 2/3. Whether you choose to use this form right here for your b or this form right here doesn't make a difference. So you go and you plug in your a and your b here, and you're going to get y is equal to a 5 cube root of 25, all in parentheses, raised to the x power.